Okay, so welcome back. This is part 2 in our series where we're going to develop this application that will allow us to use our Arduino as an oscilloscope. And you can see it's very simple. I've just got my Arduino plugged into a USB port onto our computer, and I've got a signal coming in from my signal generator, and you can see it here on the application. And this is the triangle wave coming from my signal generator through the Arduino. So we're going to develop this application. And in this part of the series, we're going to look at a very important aspect, and that is the USB communication to the Arduino. Because we're going to have to figure out how we're going to set the USB, what's the available baud rates, and we're going to find out the standard baud rate of 9600 just isn't going to work. So we're going to have to figure out how to optimize the baud rate and how to set that up. Okay, so the first thing we're going to do is we're going to look at the numbers. The best way to understand things and to do things right is to measure them and see what the real numbers are. The worst thing to do is to just go on the internet and copy and paste somebody else's code and not really understand it, but think that it makes you an expert. That's not true. So what we're going to do is we're going to understand the process going on with this oscilloscope application and what's going on with the serial port, and find out what we can do to make sure that our oscilloscope application, or any application, responds as fast as possible so we can update our screen on our C# application and update our scope very quickly rather than taking a long time. So we're going to start out with this, what's called a timing diagram. It's basically just going to give you a conceptual idea of what's going on in the process and how long the different parts of the process are taking. So you can see here I've got my C# application. What's that doing? I've got the USB connection between the computer and the Arduino. What's going on with the USB? And then I've got the Arduino itself because it's got some functions to do. So this will give you a good relative idea of what's going on, how long it's taking, what's taking a lot of time, and what can we optimize in order to make sure that our oscilloscope is updating as fast as possible. So we'll start out here. You can see in our C# or whatever, Python or whatever you want to write this in, the application is going to start out by sending a request, basically a string that's going to go from our C# application to the Arduino that says, in this case, we're going to send a string that says B100. And all that says is, okay, Arduino, the B stands for burst. Send me a burst of data as fast as you possibly can, and I want 100 samples. So I'm sending a very simple string to the Arduino over the USB. So it's going to go out, it's going to go over the USB, it's going to be very quick, it's going to, milliseconds, fractions of a millisecond to get this sent over. So it's going to be, we know that's going to be very fast. Once the Arduino gets that, it's going to start doing its job. And the job is to gather those 100 samples and store them in local arrays. Now we're going to choose that because that's the way to make those samples as fast as possible. This is basically just going to focus on grabbing a sample and storing it, grabbing a sample and storing it as fast as possible. Now the other way could be to grab a sample and go do something with it, like send it out or process it in some way, change its value. We're not going to do that. We're just going to grab samples as fast as possible, store them in arrays so we can get samples in a very short amount of time to look at higher frequency values. Once it's done putting all those values in the arrays, it now has to send those back to the computer. So the way it's going to do that, it's going to fill the output buffer. Now the Arduino has a very small output buffer of like 64 bytes, I think. So it's going to take that data and it's going to fill the output buffer, and it's going to then send those samples via this serial.println command on the Arduino. It does a background process where it fills the output buffer with some of these values and then sends it out. And once that output buffer is empty, you can fill it with more samples and send it, and fill it with more samples and send it. So this is going to take some time. We're not sure how long, but we can measure the total process and see. So as it sends it out, then it's going to transfer that data over the USB, and we're going to start out assuming we're going to use the standard 9600 baud rate. And of course, 9600 baud means 9600 bits will be sent every second, all right? So keep that in mind. We're going to use this sample rate to send over the USB to the computer. Now we're not done. Once it gets to the computer has to read the input buffer. Then it's got to process the data, because remember, the Arduino is going to be sending this in just kind of arbitrary microsecond values. So we're going to have to process those time values. And we're also going to have to process the sample values, because again, the Arduino is going to do it in 0 to 1023 equivalent values, where 0 to 1023 relates to something like 0 to 5 volts or 0 to 5.1 volts or whatever. So we're going to have to process the time and the values, and then we're going to have to plot them in our C# or whatever application. So that's going to take time. We don't know how much, but we're going to have to figure out the relative values of how long this stuff takes. Let's take an example, 100 samples as fast as possible. So we're going to send the request B100 to the Arduino. And again, it has to gather the 100 samples and store them in arrays using analog read. So the first question, how long does analog read take? Well, if you look at the documentation, each analog read to get one value is about 0.1 milliseconds, okay? So might be more, might be less, but at least that's a good ballpark. So 0.1 millisecond, we're going to do 100 samples, which means 0.1 milliseconds times 100 is going to be 10 milliseconds to get 100 samples read, okay? 10 milliseconds or 0.01 seconds to read our 100 samples. 10 milliseconds, we've read 100 samples. And if you look at this and you're thinking ahead, you might say, wait a minute, if it's going to take me 0.1 millisecond to read one sample, then what's my sample rate? How many samples will I get in 1 second? Well, if it's 0.1 milliseconds per sample, then 1 over 0.1 milliseconds tells me how many samples per second, or the sample rate. And 1 over 0.1 milliseconds is 10,000 or 10 kilohertz. So right there, it tells you the maximum sample rate here is something like 10,000 samples per second or 10 kilohertz. And if you start thinking about Nyquist and the Nyquist criteria, that's going to tell you that with 10,000 samples per second, I can only accurately measure a frequency of less than 5,000 hertz or 5 kilohertz. So now we're getting an idea, hey, wait a minute, I'm going to be limited here on what the Arduino can sample in terms of frequencies less than 5 kilohertz. So keep that in mind. That's going to be one of our limitations. So anyway, we're talking about 10 milliseconds to get 100 samples. Then we've got to fill the output buffer and send those samples. How long that's going to take, we don't know, because it's going to depend on how quickly the buffer is emptied from the USB communication grabbing that data and sending it. So that's going to vary. But when it does grab that data on the USB, we're going to look at 9,600 bits per second. How long is that going to take? Well, what are we going to be sending? We've got to figure out how many bits we're going to be sending in each sample and figure out how long that's going to take at 9,600 bits per second. So let's just say each sample is a time and a value, and let's say there's a total of 8 bytes being sent in each sample. Might be more, might be less, but at least this is a ballpark depending on the size of the numbers we send. So 8 bytes per sample and 8 bits for every byte. That means 8 times 8 bytes is 64 bits we're going to send in each sample, all right? Again, just a ballpark, but at least it gives us an idea. We're going to send 64 bits, and we're going to send 100 samples of 64 bits per sample. That means 100 times 64 is 6,400 bits are going to be sent to send all 100 samples. Now, we know we're sending at a transfer rate of 9,600 baud, or 9,600 bits per second. So how long at that rate can I send 6,400 bits? Well, 9,600 in 1 second, so 6,400 in comes out to 0.67 seconds. So you might think, wow, look at this. It took me only 10 milliseconds to gather the data, but it's going to take me, 2/3 of a second, 0.67 seconds to send that over the USB at 9600 baud. So I'm spending a lot of time sending when it's only taking me 10 milliseconds to grab the data. So we start to think, hey, wait a minute, we're going to have to do something with this transfer rate on the USB, because, you know, we're going to be waiting seconds. We got all this fast data, but we're going to be waiting seconds to actually get it to the computer and plot it. So that gives us a good idea on what we need to focus on. So let's just focus now on this USB and Arduino. We'll ignore the C# application for now and just look at, see if we can get some actual numbers. You know, how long does it take from when the Arduino receives the request to the point that it is finished filling the buffer and sending out all the samples over a 9600 baud communication link? Is there some way we can measure the time that these two blocks take to send all their data out? That will help us understand, you know, how long does this entire process take from the perspective of the application on the computer? How long does it take to request and get the data? So what I'm going to do is I'm going to go over and look at this sketch, a very simple sketch that we can use to do some basic timing and debugging of our application. And I won't go through this in detail. We'll talk about this later, but it's basically a very simple sketch that just does a void setup. Serial begins, sets it up at 9600 baud, pin mode, analog pin input. That's setting up my A0 analog input. And then it's going to go into a loop. And the loop is just going to wait if there's data available on the serial port with serial.available, then it's just going to loop through and wait for data to appear, our B100 request from the computer. As soon as that becomes available, it's going to go here and say, my receive string is whatever it reads from that read string. It's going to read that B100 and set that equal to the receive string. Then, if that receive string starts with a B, we know it's a B command that says we're going to need to grab a burst of data. If it's a B, then we're going to figure out what's the number after the B, which means how many samples does the computer want. And at this point, I'm going to start a timer so we can measure the elapsed time. We've received the B, so we're going to start a timer. It says, okay, I've received my B, and then we're going to find out how long it takes from receiving the B to sending all the data, and we're going to look at that elapsed time. So this is my timer, where I'm going to say time start is whatever microseconds after I've received my B command, and then I'm going to convert the number after this B, which in our case is going to be B100. Again, it's a string, so we have to convert it into an integer. So I'm going to take our receive string, which is what we read, the B100, and I'm going to take the substring starting at character 1, which is this B. So it's going to take the number after the B and convert that to an integer, and that's my number of burst samples. That's going to be 100 in our case. Then it's going to call this method grab, burst, and send, and feed it the 100 samples. So here's the simple method where we do the grab, burst, and send with our 100 samples. I'm basically setting up two arrays. So this represents the 0 to 1023, and this is the microsecond time for the sample. Then I'm going to go through, and in this for loop, I'm going to, as fast as possible, read my 100 samples into those two arrays. For int I equals 0 to number of samples, time I equals whatever the microsecond value is at that time. So our times, it's going to be these fairly meaningless microsecond values that we can use if we want later on. And then the value is going to be the analog read of the 0 to 1023, and that's going to go into our value array. So it's going to go through this as fast as it possibly can and fill up those arrays with times and values, in our case 100 times and 100 values. When it's done, it's going to look at sending those out with a serial print line with the time value. This is going to be CSV, comma separated value, with a time value, comma, and then a value. This is going to go through and loop through and do the sending. and then it's going to send an end string that tells the computer, okay, I'm done with my 100 samples, you can go do what you want. So after it's done with that, it's going to come back here, it's done my method, and then we're going to stop. We're going to get a stop time. It's already sent out our 100 samples, so now we can say, okay, here's the stop time. We can figure out the elapsed time from the time it received the B to the time it successfully sent out all its 100 samples. Here's the time stop. So the elapsed time is the difference. And I'm going to print to the serial port, elapsed microseconds is just the difference between time stop minus time start. So what we're doing is we're looking at these two functions plus sending it out over the serial port. And we're going to use the serial monitor to send the command and get these elapsed times back. So let's go to the Tools, Serial Monitor, and I'm set at 9600 baud down here on the serial monitor, and that's how I'm set in my sketch. So I'm going to do B100, enter, and you can see I get my data coming over the serial port. I've got the end. The elapsed microseconds is 1613324. 1.6 seconds to go through that process. Once it receives the command, it takes 1.6 seconds to gather the data and send it out over the 9600 baud serial port. So now you might think, wow, we said it's going to take 670 milliseconds or 0.67. Well, actually, we measure it to this point here, and it takes 1.6 seconds according to the serial monitor. So we're talking about some serious time, and the guess is it's mostly because of the slow transfer rate of the 9600 baud USB serial connection. So we're talking, it takes 10 milliseconds to get our samples, but to get it sent over the serial port, it takes a total of 1.6 seconds. If we want our oscilloscope to update in a reasonable amount of time, not 2 seconds to update, we're going to have to look at this baud rate and this timing and see what we can do. So it seems like if we look at this serial.begin, which tells us that we want to transfer at a rate of 9600 bits per second, can't we crank that up to get a bigger number? Well, let's look at the serial monitor and clear what we had in the last one. And you go down here to the baud rate selection, and you can see you can go from 300, 1200, 2400, 4800, 9600, 19.2, 38.4, 57.6, 78, 500,000, 1 million, and 2 million. Wow! So maybe we can crank up that baud rate to like 2 million and see what happens. So let's take a look and see if we can set this baud rate to say 2 million and see if it explodes or what happens. So we'll go here and we'll set 200. So here I've got 2 million as a baud rate. So what I'm going to do is I'm going to send that to the Arduino and see if it blows up or if it works. So it's uploading. So now let's go back to our serial monitor, and I've got 2 million as a baud rate, and we're doing the same timing as the previous one. So let's send our same B100, hit enter. Wow, that was fast. And it says the elapsed microseconds is 1, 2, 3, 4, 5, is 0.06, 0.07 seconds. So this is a huge speed up. So if you look at our timing diagram now with 2 million as a baud rate, the total time is 0.06 something seconds. So 60 or 70 milliseconds. We've got 10 milliseconds to do the reading, and the total time is only 60 milliseconds. So all of this takes a whole lot faster, and that's basically based on the serial monitor. So now we're saying 8 bytes per sample, so 64 bits. 100 samples is 6,400 bits. At 2 million samples per second, that's only 3.2 milliseconds, or 0.0032 seconds. So 3.2 milliseconds plus 10 milliseconds, we're talking about 13 milliseconds. Plus additional timing, we're talking about 60 or 70 milliseconds if we take advantage of that baud rate of 2 million. Okay, so now that we have looked at the slow transfer rate on the USB and fixed that, there are some other issues we really need to look at and address, because those can in fact be even worse, have an even worse impact than the slow USB. And some of those involve some of the characteristics or capabilities of the Arduino. For example, you may be aware that there's not a lot of RAM on the Arduino to store your variables. So for example, if we grab a big burst of data, we're going to have to store that on the Arduino, and if it doesn't have enough RAM, we're going to have to figure out how we're going to deal with that. And those Arduino experts out there may have noticed in the sketch we just did, we intentionally left out one aspect of this whole timing situation on the Arduino side that can actually have a worse impact than a slow baud rate and slow things down a lot. So in the next video, we're going to take a look at some of those Arduino characteristics and see how we can deal with them. And we're also going to look at some general characteristics of an oscilloscope and some of the timing aspects and how we can get everything to work, so that you see here where it's a fast update. So anyway, if you like any of these videos, I encourage you to like and subscribe and hit the bell notifications, and most of all, let others know that we're here. That would help a lot. Appreciate it. Take care and have a really good day. Thanks.